Hello and welcome to this Thermo Fisher Scientific presentation about the rheology of polymers. In this presentation I will give an overview of common rheological testing methods for polymer melts, solutions, as well as solid samples. Furthermore, the application-related information that can be gained from these tests will be discussed. I will close this presentation with a short overview of different rheometer configurations and accessories specifically for testing polymers. But let's start with the question, what are polymers and why are they so important for our everyday life? Polymers are large chain-like molecules that consist of repeating monomer units. They can be either synthetic or of natural origin. We are surrounded by polymers almost everywhere, and they affect many aspects of our life. Biopolymers, like cellulose, starch, proteins, or DNA, can be found in all living things. In food or personal care products, polymer additives can act as thickeners, stabilizers, or gelling agents. Examples for this are xanthan or guar gum. A lot of cosmetic products contain polyethylene glycol, which serves different purposes like emulsifier, stabilizer, or thickener. Solid polymers are used for packaging, automotive parts, construction materials, and many other things. Frequently used commodity polymers include polystyrene, polyethylene, or polyvinyl chloride. As a melt, or when dissolved in a solvent, polymers form random coils and build very strong intermolecular interactions through entanglements. Due to the complex molecular structure, many polymeric fluids also show a complex flow and deformation behavior. Rheology is the study of flow and deformation of all kinds of matter, and polymer rheology deals with the investigation of the complex flow and deformation behavior of polymeric samples. Polymer melts and polymer solutions are so-called viscoelastic fluids, which means that they have viscous as well as elastic properties. The high elasticity of many polymer fluids can lead to several flow anomalies, which can cause unwanted effects during polymer processing. Examples for this are shown at the bottom of the slide. They include die swell or the formation of an uneven shark skin when the polymer is processed through a narrow die. Polymers can occur in different forms and states. When dissolved in water or any other solvent, they are frequently used as thickeners or stabilizers in many products. These include processed food, personal care products, drilling fluids for oil production, paints, inks and coatings, or superabsorbents. When brought above their glass or melt temperature, polymers form viscoelastic liquid melts. True melts are formed by thermoplastic materials which contain non-cross-linked polymers only. Thermoplastic polymers can be either amorphous or partly crystalline. Amorphous thermoplastic materials become soft when their glass transition temperature is exceeded. Partly crystalline thermoplastic materials go in a so-called rubber elastic state when the glass transition temperature is reached. Above the melting temperature, they form a high viscous liquid melt. The rheological properties of polymer melts are important for many processing applications. Below the melting or the glass transition temperature, polymers are highly elastic solid materials. They can be differentiated by the degree of cross-linking between the individual polymer chains. Thermoplastic materials do not show any chemical cross-linking. Thermosets and elastomers are chemically cross-linked materials. Thermosets show a very narrow and elastomers a very wide meshed structure. As shown on this slide, depending on its state, rheological measurements can provide many informations about a polymer. They can be used to get information about the degree of crystallinity of a polymer, To determine transition temperatures, like the glass transition or the melting point, calculate molecular weight and its distribution, find the optimal processing conditions, determine the application properties of final products such as stiffness, brittleness, damping behavior or impact resistance, investigate the kinetics of curing and cross-linking reactions, or get information about degradation and decomposition conditions. Rheological measurements are usually carried out by applying either a rotational, an oscillatory, or an extensional flow field. Rotational tests are used for measuring the shear viscosity, normal stress differences, as well as yield stress or thixotropic behavior of a material. Oscillatory measurements can be used to investigate viscoelastic behavior, measure the complex viscosity, or to investigate the stability of a material and to determine phase transition temperatures. Extensional flow occurs in many technical applications and can be investigated with rheological extensional testing methods. The results of these tests will provide information about the extensional flow behavior of a material, which can differ significantly from the behavior under oscillatory or rotational shear flow. For highly elastic polymer liquids or solid and semi-solid polymers, applying an oscillatory flow is the most common testing method. On this slide, the relationship between the zero shear viscosity of a polymer melt and its molecular weight is shown. The zero shear viscosity is the constant viscosity of a polymer melt at low shear rates. As can be seen here, for polymer melts, the zero shear viscosity strongly depends on the average molecular weight. Below a critical molecular weight, the zero shear viscosity is directly proportional to the average molecular weight. Above the critical molecular weight, the polymer starts to form entanglements and the zero shear viscosity is increasing exponentially with an exponent of around 3.4. If, for a given polymer, a specific correlation factor is known, the average molecular weight can be calculated directly from the zero shear viscosity. Correlation factors for many thermoplastic polymers can be found in literature. The value for the critical molecular weight depends strongly on the molecular structure and varies for different polymers. Polymer melts are usually shear thinning materials. When exposed to low shear rates, they will show a so-called Newtonian viscosity plateau. This constant viscosity is also referred to as zero shear viscosity. Once a critical shear rate is reached, the melt viscosity will start to decrease. The average number of entanglements formed between the individual polymer coils is decreasing with increasing shear rate. This plot shows the master curve of a polystyrene melt. In order to obtain this curve, several frequency sweep experiments were performed at different temperatures. For each frequency sweep, the complex viscosity was recorded, and afterwards the time-temperature superposition principle was used in order to shift the individual curve to a fixed reference temperature. According to the so-called Cox-Mertz rule, the complex viscosity derived from oscillatory frequency sweep measurements and plotted against the angular frequency omega is equal to the steady-state shear viscosity from rotational testing plotted against the shear rate gamma dot. The Cox-Mertz rule is an empirical rule that is valid for many polymer melts and polymer solutions. The viscosity curve is now showing data over a wide shear rate range and can be divided into three ranges. At low shear rates, we find the constant so-called zero shear viscosity. For polymer melts, the zero shear viscosity can be used to calculate the average molecular weight when a polymer-specific correlation factor is known. At a medium shear rate range, we see the onset of shear thinning and the viscosity starts to decrease. The width of this transition range correlates with the molecular weight distribution of a polymer. This range also provides information about the relaxation behavior of the polymer. At high shear rates, the viscosity is decreasing with a constant slope in a double logarithmic plot. In this range, the viscosity is independent of the molecular weight. The viscosity at high shear rates is of interest because in many processing techniques the material is exposed to such shear rates. Some examples are shown here. In order to generate viscosity data for a polymer melt over a wide shear rate range, different measuring techniques are available. Low shear rate data can be obtained from creep and recovery tests as well as steady-state rotational experiments. When applying the Koch-Merz rule, oscillatory frequency tests usually provide viscosity data in the medium shear range. All those tests can be performed with a rotational rheometer, which is the most versatile instrument for polymer rheology. High shear viscosity data can be directly measured with instruments that use a capillary flow. An example for this is the viscosity measurement in the backflow channel of a microcompounder, like it's shown here on the right. In order to obtain viscosity data over the entire shear rate range, the time-temperature superposition principle can be applied. Details about this will be explained on a later slide. The reason why rotational tests in many cases only provide reliable viscosity data in the low shear rate range is shown here. On this plot, we see the viscosity data for a low-density polyethylene tested at 180 degrees C. The red symbols present data that was obtained from a rotational test, while the green symbols show the results of an oscillation frequency sweep. When plotted against the angular frequency or the shear rate respectively, the results from both tests overlap in the low shear rate range. This confirms that the Koch-Merz rule is valid for this sample. However, once the Newtonian plateau is left and the viscosity starts to decrease, we can see that the shear viscosity from the rotational test starts to drop dramatically and doesn't show a smooth progress anymore. The complex viscosity from the oscillation frequency sweep test delivers smooth data up to higher frequencies/shear rates. The reason for the unsteady behavior and the apparent drop of the shear viscosity during the rotational test is sample fracture caused by secondary flow fields. This is due to the high elasticity of the polymer sample. When these phenomena occur, the geometry of the rheometer, in this case a parallel plate setup, is not filled correctly anymore and the recorded viscosity data becomes false. This effect occurs for many polymer melts already at relatively low shear rates. Since the Koch-Merz rule is valid for most unfilled, non-cross-linked polymer melts, the complex viscosity derived from oscillation frequency sweeps also provides correct information about the shear rate depending viscosity. As already mentioned, the viscosity of a polymer melt correlates strongly with its average molecular weight. On this plot, the shear rate depending viscosity of 3 different low-density polyethylene samples is presented. The red symbols show the viscosity data for a high molecular weight polyethylene. The green symbols present the viscosity for a low molecular weight polyethylene. And the blue symbols show the viscosity for a blend of the other two polyethylenes in a 1:1 ratio. Several things can be observed here. First, the zero shear viscosity is increasing for the higher average molecular weight samples. The width of the Newtonian range is getting smaller for the higher average molecular weight materials. At high shear rates, the viscosity values for the 3 polymer samples are converging. At even higher shear rates, outside of what is presented here, the viscosity for all three samples would be the same. When the shear rate reaches a critical value, the viscosity of a polymer melt will start to drop. In a double logarithmic plot, the width of the transition between Newtonian behavior and decreasing viscosity at a constant rate depends on the molecular weight distribution or polydispersity of a polymer. A polymer sample with a narrow molecular weight distribution will show a sharp and narrow transition. A polymer sample with a broad molecular weight distribution, on the other side, will exhibit a very broad transition range. For many polymer processing techniques, a broader distribution with a smooth transition between Newtonian behavior and shear thinning is preferred. In order to determine rheological parameters that describe the viscoelastic behavior of a polymer melt, usually tests and oscillation mode are used. Viscoelastic parameters include the storage and the loss modulus, G' and G', as well as the loss angle delta and the loss factor tangents delta. During such a test, the sample is exposed to either an oscillating sinusoidal strain or stress signal. The response of the sample to the external excitation is a stress in case of an applied strain or a strain in case of an applied stress. For low excitation amplitudes, also the response of the sample will show the shape of a sine wave. For viscoelastic materials, the excitation and the response signal show a phase shift between 0 and 90 degrees. The maximum amplitudes of both sine waves and the phase shift are used to calculate G' and G'. G' is a measure for the elasticity of a sample, and G' a measure for its viscosity. Different types of rheological tests in oscillation mode are available. In an amplitude sweep test, the amplitude of the applied stress or strain signal is gradually increased while the excitation frequency is maintained constant. The amplitude sweep test is usually used to determine the so-called linear viscoelastic range of a sample. In a frequency sweep test, the amplitude of the excitation signal is kept constant while the frequency of the signal is either in or decreasing. Frequency sweeps are used to investigate the viscoelastic behavior of a material at different timescales. During a temperature sweep test, amplitude and frequency of the excitation signal are constant while the temperature is changing. This test is also known as dynamic mechanical thermal analysis. It can be used to determine temperature-depending structural changes and phase transitions of a material. In a time sweep, all rheological conditions are kept constant and only the structural changes of a sample over time are monitored. Time sweeps are used to measure the relaxation or stability of a sample, as well as for the investigation of curing and cross-linking reactions. Here you see the results of an amplitude sweep test performed with a low-density polyethylene sample at 190 degrees C. G', G', and the tan delta are recorded as a function of the applied deformation. With G' bigger than G', the sample is behaving predominantly viscous. At low deformation, the rheological parameters are constant and independent of the applied strain. This region is the so-called linear viscoelastic range. In this range, the applied strain values are so small that the microstructure of the sample is not changing and the measurement is considered non-destructive. Once a critical deformation is reached, the rheological parameters start to change. For most polymer melts, a drop in G' and G' is observed. At high deformations, the sample is outside its linear viscoelastic range. When we have a look at the raw data of the amplitude sweep test, which are the sinusoidal waves of the excitation signal and the response signal of the sample, we can see that within the linear viscoelastic range, both exhibit the shape of an undeformed sinusoidal curve. The Lissajous plot represents the relationship of the stress and the strain signal for a single sine wave. Within the linear viscoelastic range, it shows the, for a viscoelastic sample, typical ellipsoid shape. Outside the linear viscoelastic range, the excitation signal, which is in this case the deformation, still has the shape of an undeformed sine wave. However, the response signal of the sample, in this case the stress, is now a distorted sine wave. Accordingly, the Lissajous plot also shows a deformed shape compared to the linear viscoelastic data. The evaluation of the raw data for an amplitude sweep test presents another way to investigate the rheological behavior of a material. However, the main reason for performing this type of test is to determine the linear viscoelastic range. This information is needed for other types of rheological tests, such as a frequency sweep, which are supposed to be performed within the linear viscoelastic range of the sample. Frequency sweep tests are used to determine the viscoelastic behavior of a sample at different timescales. The low frequencies correspond with the long time periods, while the high frequencies correspond with extremely short times and fast processes. The data shown here present the results of a frequency sweep test with a polystyrene melt performed at 190 degrees C over a very wide frequency range. The plot can be divided in three regions. At the low frequencies, we see the so-called terminal region, where the melt is predominantly viscous. The behavior in this range is governed by long molecule chain relaxation processes. In the terminal region, G' and G" have the typical slopes of 2 and 1 in a double logarithmic plot. At medium frequencies, we see a transition region with a crossover between G' and G". The behavior in this range is strongly affected by the molecular weight distribution of the polymer. At the highest frequencies, the sample behaves predominantly elastic, with G' bigger than G". The polymer behavior in this range is governed by the fast relaxation motion of the shortest polymer chains. The location for the crossover point of G' and G" in a frequency sweep is strongly affected by the average molecular weight and the molecular weight distribution. For higher molecular weight samples, the crossover shifts further towards low frequencies and the predominantly elastic behavior becomes more prominent. A broader distributed molecular weight will shift the crossover point to lower modulus values. Since the frequency sweep is very sensitive for changes in the molecular structure, it can be used to detect changes caused, for instance, by thermal decomposition. In a series of repeating frequency sweep tests, the location of the crossover will start to shift if the polymer is not stable under the test conditions. Frequency sweep data over such a wide frequency range, like it was presented on the slide before, cannot be obtained from a single experiment. Usually, between 2 to 4 orders of magnitude in frequency are covered in a single frequency sweep test. On this slide, you see the results of a frequency sweep with a polystyrene melt performed at 190 degrees C. Data at lower frequencies is usually not available due to the dramatically increasing test time. In this range, a single oscillation can take up to 20 minutes or even longer. The highest achievable frequencies are limited by the rheometer itself. Frequencies of around 100 Hz or 628 radians per second are usually the upper limit. In order to extend the measuring range towards higher and lower frequencies, the so-called time-temperature superposition principle can be used. For this, frequency sweeps in the limited frequency range are performed at different temperatures. In this example, the polystyrene melt was tested at 150, 190 and 230 degrees C. One of these temperatures is now selected as a reference temperature, and the data obtained at the other temperatures can be shifted towards the reference curve. This is possible since frequency and temperature are affecting the sample's behavior in a similar way. At lower temperatures, the polymer behaves like it is exposed to higher frequencies. And at higher temperatures, it behaves like at lower frequencies. The individual curves are usually shifted horizontally only. Once the shift was performed by the rheometer software, a single frequency sweep over an extended frequency range is obtained. The time-temperature superposition principle cannot be applied to all samples, but it works for many thermoplastic polymer melts over a limited temperature range. G' and G" data acquired over a wide frequency range can be used to calculate the molecular weight and the molecular weight distribution for many linear thermoplastic homopolymers. For this, the tested range must include data from the terminal region up to the end of the plateau region. Since the first mentioned is usually easier to obtain with frequency sweep tests, this rheological method is particularly helpful to obtain information about the higher molecular weight fraction. Rheological tests in oscillation performed over a wide temperature range are used to determine characteristic transition temperatures of a polymer, such as the glass transition or the melting temperature. On this slide you see the results of a temperature sweep experiment with a polyether ether ketone. The test was performed over a temperature range of more than 300 degrees C. At the lowest temperature, the polymer is a solid material in its so-called glassy state. The rheological parameters change only very little with temperature and are independent of the molecular weight or the degree of crystallinity. Polyether ether ketone is a semicrystalline polymer. That's why it shows a glass transition at a specific temperature. Once this transition temperature is reached, the polymer starts to become softer and the G' signal starts to drop. The glass transition does not occur at a single temperature, but rather over a temperature range. In this range, G" as well as the tan delta go through a maximum before they drop again. In rheology, it is common to use the maximum in G" to indicate the glass transition. But it is also possible to use the maximum in the tan delta or even the onset of significant drop in the G' signal. Therefore, it should be indicated which method was used when a glass transition temperature is presented. After the glass transition is completed, the polymer goes over in a so-called rubber elastic state. Especially for semicrystalline polymers like polyether ether ketone, the behavior in this range is dominated by its elastic properties. At even higher temperature, the moduli will start to drop again significantly and the polymer becomes a melt. At the melt temperature, indicated by a crossover of G' and G', all crystalline domains inside the polymer disappear. Only semicrystalline thermoplastic polymers exhibit a melting temperature. Purely amorphous polymers go only through a glass transition with no further melting point. Besides for measuring the phase transition of a polymer, Temperature sweep tests are also useful for finding the ideal processing temperature range of a material, as well as for investigating the properties of solid samples, like brittleness, stiffness, or the damping behavior. On this slide, the general behavior of polymers in a temperature sweep or dynamic mechanical thermal analysis is shown for G'. Semicrystalline polymers go from a glassy region over a rubbery plateau into the melt state. The height of the step from the glassy region to the rubbery plateau depends on the degree of crystallinity of the polymer. Low molecular weight polymers do not exhibit a rubbery plateau. Once the glass transition is completed, the material becomes a soft melt and G' is decreasing with increasing temperature. Cross-linked polymers, on the other side, do not melt, but will stay in a rubbery state until thermal decomposition occurs. Besides rotation and oscillation, extension is the third type of flow that can be investigated with rheological methods. Extensional flow occurs during many technical processes, such as spraying, filling, or more related to polymer melts, film blowing, and foam extrusion. This slide shows the general behavior of complex fluids in an extensional flow field. At low shear rates as well as low extensional deformation rates, polymeric materials show a Newtonian behavior. The relationship between extensional and shear viscosity is described by the so-called Troughton ratio, which is, in case of uniaxial extensional deformation, 3. This means that the extensional viscosity for the same sample is 3 times higher than the shear viscosity. Once a critical deformation rate is reached, polymeric materials show a thinning behavior under shear flow, but exhibit strain hardening under extensional flow. On this slide, the transient extensional viscosity at different extensional deformation rates is presented for 2 different polyethylene samples. The tests were performed with a special film stretching fixture for rotational rheometer, like it's shown on the right. The upper plot presents the results of extensional tests with a non-branched, high-density polyethylene sample. No extensional hardening can be observed for this type of material. The lower plot shows the results of the same experiments performed with the highly branched, low-density polyethylene. For comparison, the red curve shows the transient shear viscosity multiplied by 3. This data was obtained from rotational step experiments. It can be seen that the extensional behavior for this sample differs quite significantly from the behavior in shear flow. Especially for the higher deformation rates, strain hardening is observed. Strain hardening behavior can have a positive effect on polymer processing techniques like film blowing or fiber spinning. Having a good understanding of the extensional properties of a polymer sample is therefore helpful to optimize the final product properties for such techniques. And with this, I'd like to close the applied rheology part of this presentation and summarize the most important information before we move over to a short rheometer and rheometer accessory overview. Polymers play an important role in many aspects of our everyday life and occur at different states. Rheological tests can be used to investigate the complex flow and deformation behavior of polymer melts, solutions, as well as of solid polymers. Under shear, polymer melts usually show a shear thinning behavior when a critical shear rate is exceeded. Tests with an imposed oscillatory deformation or stress signal are used to investigate the viscous as well as the elastic properties of polymers. The results of rheological experiments are used to find ideal processing conditions, investigate thermal stability, determine phase transitions, or measure final product properties of polymers. Besides rotational shear and oscillation, extensional flow plays an important role for many technical applications and can also be investigated with rotational rheometers. In the second part of this presentation, I would like to give a brief introduction to the thermoscientific HAAKE mass rheometers and their configurations and accessories for investigating polymeric samples. The thermoscientific HAAKE mass instruments are high-end rheometers for research and development as well as advanced quality control and routine measurements. The upper and lower electrical temperature control units allow for testing polymer melts up to temperatures of 400 degrees C. All measuring geometries include an upper rotor made of titanium and a ceramic material. The lower part, made of titanium, minimizes inertia effects, and the ceramic shaft reduces thermal conductivity and enables fast temperature setting of the sample. For an even wider temperature range and the possibility of attaching fixtures for solid sample testing and extensional rheometry, the HAAKE mass can be equipped with the Controlled Test Chamber (CTC). It allows for performing rheological tests up to a temperature of 600 degrees C. When the low temperature option is used, the CTC can be cooled down to -150 degrees C with liquid nitrogen. The CTC consists of two temperature chamber half shells that can be moved individually on a rail system. For sample loading, cleaning, or changing the measuring geometry, the CTC half shells can be moved into the so-called parking position at the rear left side of the rheometer. In the parking position, the operator has full access to the sample and the measuring geometry without the danger of touching the hot or very cold inner part of the CTC. Since the CTC is fully closed when in parking position, the internal temperature can be controlled and maintained during cleaning, sample loading, or geometry change. When in the measurement position, the two half shells of the CTC enclose the measuring geometry completely, what allows for a homogeneous and gradient-free temperature control of the sample. As a hybrid system, the CTC combines the advantages of convection heat transfer, which is a homogeneous temperature distribution, with those of radiation heat transfer, which is the ability of rapid temperature changes. For the HAAKE mass and the CTC, various standard parallel plates and Conan plate measuring geometries with different diameters are available. The lower part of the measuring geometry is mounted on a lower holder with an integrated temperature sensor. The lower plates are designed to collect surplus material during sample loading or when a material is expanding during a measurement. All upper plate and cone rotors are made of titanium and a ceramic material for the rotor shaft. For the investigation of curing reactions or for testing abrasive materials, disposable parallel plates geometries made of aluminum are available with different diameters. With the solids clamping tool, solid polymer specimen can be tested up to close to their melting temperature. Phase transitions, like the glass transition, as well as the properties of solid materials such as stiffness, brittleness, or damping properties can be investigated using the solids clamping tool. For investigating UV curing reactions at elevated temperatures, a special lower holder with a quartz glass plate and a lower connection port for your UV light guide is available. A UV light source can be triggered by the rheometer control software. A parallel plate setup with the DEA comp sensor integrated in the lower plate allows for the simultaneous performance of rheological measurements and dielectrical analysis up to temperatures of 220 degrees C. Typical applications that can be investigated with this method combination include the curing behavior of reactive thermosets or composites, adhesives, coatings, and dental materials. The SER tool transforms the rotational shear rheometer in an extensional rheometer for polymer melts and semisolids. The measuring principle of the SER tool is based on two counter-rotating wind-up drums that are applying an extensional deformation to an attached sample. For a deeper understanding of structure property relationships, usually more than one analytical technique is required. When combining rheometry with other analytical techniques, additional information can be obtained. This allows for an extended investigation of a material and provides a more complete knowledge of its characteristics. The HAAKE mass rheometers can be coupled with an FTIR or a Raman spectrometer for simultaneous rheological and spectroscopic analysis of a material. The FTIR coupling can be used, for instance, to investigate the deformation and orientation of molecules as a function of shear, or to study the kinetics of curing and cross-linking reactions. With the Raman coupling, changes in the crystallinity of a polymer melt during a rheological experiment can be monitored. The Thermo Scientific HAAKE Minilab 3 is a small-scale conical twin-screw extruder that enables the compounding and processing of sample quantities down to about 7 milliliters. It is equipped with a backflow channel and a bypass valve, which allows for controlling the residence time of a sample inside the compounder. The patented design of the backflow channel consists of a slit capillary with two pressure transducers that are used to measure the pressure drop inside the flow channel. When a sample is passing through the flow channel, the resulting pressure drop can be used to calculate an apparent shear stress. From the selected screw speed and the measured back pressure, an apparent shear rate can be obtained. The shear stress and the shear rate values can be used to calculate the relative sample viscosity at different screw speeds. This principle enables to determine the shear thinning behavior of polymer melts. The Thermo Scientific HAAKE MiniJet Pro is a piston injection molding system that can be used for the preparation of solid specimens for rheological tests. Test specimens can be produced from powders, pellets, or a direct melt transfer from the extruder die. Several mold designs are available, allowing for the preparation of many different types of sample specimen, including disc shapes for parallel plate geometries and rectangular bars for dynamic mechanical analysis with the solids clamping tool. And with this, I'm going to end this presentation about applied polymer rheology. I thank you for your attention and would like to refer you to our website in case you have further questions about our products or rheology and extrusion in general. Goodbye.